I'll just use it. No worries. All right, hey everyone. Thanks, Harsh, for such a great introduction. I don't think I deserve that much, but okay. Cool. Nice. Hello everyone. My name is Kautuk, and I've been working on the scaling side of things since a couple of years. That's something which I'm most passionate about, and my aim is to actually, make Web3 accessible and like give it in the hands of like the most usual users that are out there. Just everyone out there. So yeah, that's why I want to scale Ethereum so that it becomes as easy and intuitive for everyone to use. So the topic is scaling Ethereum with rollups and how this might look like in the future. So it goes over what the current state of rollups are and how rollups will be evolving and what kind of new things that we can see coming. So a little about myself. So I work at the PSC team, which is a small group inside Ethereum Foundation. So I have worked on Hubble Optimistic Rollup and right now working on DLS Wallet. Other than that, I have worked with LifePeer and I have moved their protocol from mainnet to Arbitrum. So I built the data and liquidity bridges for them. And quite recently, I started working on Stacker Network, which is a personal project. And yeah, I'll talk about it a little later. So before that, all opinions are my personal and that are not representative of EF in general. So cool. So why scale Ethereum? So basically there are two reasons for it. So which is to decrease the network congestion and also to increase network throughput. So what happens when the network is congested is that the gas prices shoot up high and like nobody is able to get their transactions in and everything like that. And the other part is increased network throughput. So right now Ethereum does around 15 to 20 transactions per second. With rollups, it's able to do like around 100 or 200 or some other use cases push it to 1,000. But other than that, it's still very less as compared to generic use cases like Visa, which does like hundreds of thousands of transactions per second. So that is why we need to scale Ethereum so that it's able to support all of this. It's not only about the gas price and everything, but also to support like more regular use cases like I just mentioned. So how rollups help? So why I'm jumping out to rollups? Because I think now it's quite established that rollups are the best possible scaling solution in the medium term. There were other proposals like Plasma, sidechains, and everything, but right now I think the general consensus is that rollups work the best. So it moves compute away from the mainnet. So whatever computation that happens on mainnet, it happens off-chain. And while doing so, it stores enough data on-chain to verify the same compute. So even if the compute is happening off-chain, it still maintains a decent amount of state so that you can rebuild the transactions. So what I mean by that is essentially rollups replace compute with data. Now the question arises that the data is the most expensive part on-chain. So isn't that very expensive to do? So that's where rollups are smart because the data only needs to be in a read state because you don't immediately execute whatever is there on rollups. So you just store the data in call data. Call data is basically the function parameter, which is like non-modifiable and non-persistent, and it is much cheaper than the native storage. So this is a similar, a basic how rollups store data. So you just have a function which calls call data, and you just don't do anything with it. Like this is a very basic example. It doesn't do much. It just saves the store state root. But like if you're building a formal rollup, you do like batch indexing and everything. But the most important part is the transactions aren't used inside the function body. So this is how a simple rollup mechanism looks like. So pardon me, I just got to know about this talk yesterday and I hand drew all the sketches, so it might be a little weird. So what happens at any L1 block, you just have a event which off-chain entity reads, and it creates a local state. So on the L2 side, you have inputs which modifies the local state and you get to a final state, and you package this final state together and post it back on L1. So how this packaging works is basically what differentiates different rollups, which we'll be talking about, which is the flavors of rollups. So we have optimistic rollups and we have ZK rollups. Just wanted to quick check, how many developers are there in the house? Cool, nice. I get excited by it. So this is how optimistic rollups work. So what happens is on L2, you have a state, there is a transaction, it moves to a new state, then there is another transaction, it moves to another state, and this is the final transaction. In optimistic case, what happens is you take all the transactions as it is, then you take the final state and you post it on chain. So over here, it's in red. Basically, the state is not final yet. There is a 7-day waiting window where anyone could just dispute the transaction that, okay, this is not great. The transactions are not right. What you posted is just rubbish. So if that's the case, the state remains at S3. Before rolling back, the state was S1, and after rolling, it becomes S3, but it's not final. But after a 7-day window or whatever the rollup chooses to do, it becomes green, which means it's finalized. Similarly, in ZK rollup, what happens is instead of storing the inputs directly, there is some magic that happens. I don't understand the ZK math, so I just call it magic. So there is a magic that happens, and it creates a ZK proof of all the transactions and the compute that happened, and then you store that on chain, and it is immediately finalized because magic, right? Basically what happens is that it creates a ZK snark. That snark is basically representative of what the transactions happened, and if there is any particular thing that went wrong, the proof won't match. So that's why we think that it gets final right now, and that is the benefit of ZK over optimistic, that it finalizes things very quickly. There are two more types of rollups which are like recently coming up, which is a sovereign rollup which just posts data on chain but doesn't have fraud proofs, and there is this Validiums which is a ZK flavor of sovereign, so they just post the proof online, the final state on chain, and the data availability is off chain. But personally, I think that these are not exact L2s; these are pseudo L2s. So how to build your own optimistic rollup? So has anyone here built a rollup before? Show of hands, or someone who knows how to build a rollup? Cool. I think I'm going to change that now. So there are just these 4 steps that you need to do. Emit an event for an on-chain activity. It could be anything. This is the state basically which you want to roll up to. Then listen to this event off-chain and create a local state for it. So let's say there was an escrow contract. You send some you send some tokens to the escrow contract, and that emits an event, and you just use this data on off-chain. Do whatever you want to do with this state locally, and then what you do is like you write the logic of how the state is changed. And then once that is done, post the new state on chain along with inputs that cause the mutation. So what it looks like in practice is like this is a deposit contract which just like accepts ERC20, and once the tokens are deposited, it emits an event. Then you listen to the event off chain. So it does like a account registered event listener, and then what you do is you create a state off chain. So what it essentially looks like is a Merkle tree. So there was this address 0x1234 that deposited 10 tokens. Then there is another account which is ABCD which deposited 8 tokens, and you create a Merkle tree. This is all off chain. Nothing is happening on chain. Then what happens is that you make some transactions. So basically what this is doing is transferring 4 tokens from first address to the second address, and you can see that there is a new state. And also if you see that there is some compression going on, so instead of using the whole 40 characters of the address, I can just replace it with a Merkle tree, and this is what Rollups does. They compress the data, and this is what you can do, whatever you want to do. And once that is done, you just send this transaction to L1. So again, you can see this is a very basic code, not representative of real world, but you can see that the leaves and the transactions are stored as call data, and it emits a batch submitted event. And on chain, it looks like this. So earlier, the contract knew that it was in a red state. Then this transaction happened, and this is in a new state, which is the blue state. So yeah, that's mostly how rollups work. People make it very complicated that, okay, there is a optimistic rollup, there is optimism, there's Arbitrum, you deploy contracts and everything. And that is, I think, the most, misinformed part about rollups. So after seeing this, how many of you think that it's not very difficult to build a rollup? Yeah, nice. So everyone can build a rollup on their own. You don't need to rely on stuff. The other thing that comes up is how fraud proofs mechanism works. So you do everything, you post data on chain, what now? So you need to have some security of that data, you need to validate that data. So what you do is you write the same logic that you did off chain, so basically the Merkle tree logic, and you just store it in a contract. You don't need to run everything, you just store it in a contract. And once the data is stored on chain, which is in the red state, the red S3 state, you read deposits and batches step by step from the time it occurred, and then you rebuild the state using the same logic, and you compare the generated final state with the off-chain state. If the 2 states match, then that is great, but if it doesn't, you can just raise a dispute that, okay, this guy did some shady stuff, you need to roll back. So rollback is basically from the new state, you go back to the previous state and eliminate all the transactions that came in. That's all. That's what about rollup. So like I said, rollups are misunderstood a lot. So what I mean by that is there doesn't necessarily need to be a chain or implement a VM. So up until now, the idea is that we'll have a contract which will run in a VM, and that VM will do some stuff and then post data on chain and yabba yabba. So that's not entirely true. So there are 2 basic rules of building a rollup. You define a deterministic state and state transition function. So in the previous example, it was a Merkle tree. That was the state. The Merkle root was the state. And the state transition was how the leaf Merkleizes. And then you take the input which caused the state mutation plus the final state and post this data on chain. That's all. So rollups are essentially simple state machines. So you must have, if you have an engineering background, you must have learned about state machines, how they work. So rollups are exactly that. And this can be extended to both EVM and non-EVM rollups. So EVM basically implements a state tree, and that state tree is basically what the state is, and the state transition is how the state tree is mutated, and that's how Optimism does it, that's how Arbitrum does it, that's how zero-knowledge rollers are trying to do. Now let's talk about the future of L2 scaling. So all of this was great. That's the situation right now. And yeah, there are some, these are working great, but this is still not up to the mark wherein like you can actually run like generic Web 2 applications with it. So we have some examples. Anyone can identify what's the common thing between them? Cool. So all of these flavors of all of these rollups are EVM compatible, right? You can take a contract and then just deploy in it. The first two are optimistic rollups, and the last three are zero-knowledge rollups. And interestingly, all three of them are the first zero-knowledge EVM rollups. Then there is a rollup called Starknet. What you do is they have a different execution environment. You write Cairo code, and then that Cairo contract compiles down to machine codes, and that works. So Solidity, Cairo. We have another flavor of rollup, which are these, which is loop ring, DYDX, Aztec, immutable X. These rollups are not exactly platforms. You cannot build on top of them, but these are still rollups because they do what they want to do. So these are very, very specific to the type of thing that they are trying to do. And this is why I categorize them as the future of rollups, which is basically application-specific rollups. So application-specific rollups, what they are and how they function is that they are full rollups that serve a singular purpose. That could be like just token transfers or just NFT transfer or something like that. They are usually standalone and independent. So if you have a rollup that does like DYDX doesn't care about what games that you can build on top. They're just focused on doing exchange stuff. They are highly efficient for the single use case and may or may not interact with other chains or like other rollups. So this is 4 basic points of application rollups. And what that essentially means is that they are tailor-made to your use case using whatever design choice that you make. So you may not want to use EVM. You may want to use like a rollup that is very, very efficient in, let's say, trading. You want to do something which is very efficient in like building and chain, building games. So that is a very basic use case for them, and they independently scale up and down based on demand. So if there is a lot of congestion on a particular rollup, you can just scale that independently as compared to other rollups. And I have a really cool example afterwards. And they are unaffected by traffic on other apps. So if let's say, you must have observed like a lot of NFT minting programs go on, and because of those minting programs, there's a huge spike in gas fees, and you just can't transfer ERC20 or like normal Ether at the same price that you used to do because some other rollup is doing NFT minting. So they are very efficient. So I used to work on this project called Hubble, and you can see that last year we ran some numbers, and it was the cheapest rollup out there to do ERC20 transfers. So this rollup is now used by WorldCoin for their infrastructure. So they have like UBI tokens, and they just do ERC20 transfers. So that's like a very specific use case. So you can see it's like even I think 5 times or 10 times cheaper than the most prominent rollup. They are independent. So if you remember Arbitrum Odyssey event, everyone was doing minting and stuff. So what happened was the participants of the Arbitrum Odyssey applications, they were getting a lot of traffic. And because of that, there was a huge gas price hike on L2. That was the most severe case, and that did not happen afterwards. But it was so bad that the team had to shut down their entire program and wait for there to upgrade to Arbitrum Nitro, and then that's still not activated back. So the other applications were largely affected by it. So this is a piece stolen from Twitter. So we know about Cosmos. So you guys must have heard about Cosmos, right? So they allow you to build independent L1s. But why independent L1s are not great as compared to independent L2s is that they have low security, they don't have atomicity, and they don't have that network effect to go on, to be honest. Ethereum already has like a really nice network. You can have good exchanges, you can have good lending, borrowing protocols and stuff. It's very difficult to do that with independent L1s. So there are also a couple of changes that are supported at the core level. So there are 2 EIPs which wants to help out on on that further. So for it, it reduces the call data cost. So right now it's, I think, 16 gas per byte, but it needs to be reduced to 3 gas per byte. But a better proposal came up, which is proto-dank sharding. So what it does was it will replace call data with temporary data blobs, and these blobs are larger in size, but they are much cheaper, and they are cheaper because they will be eliminated after a month of use. The idea is that these blobs will be indexed by independent sequencer, independent archive nodes, and you can just call that blob from there. Then there is compression schemes, like this is what BLS signature scheme looks like. So in normal ECDSA, you have a transaction signature. But with BLS, what you can do is you can combine all the transactions and you can just have one signature. So this considerably reduces the data cost. So everything is good and all, but like, how many of you are still convinced that they want to build a rollup? But like, you don't want to focus on that. You have limited resources. You want to focus time on building the application, not the infrastructure itself. So DYDXs are great, they are huge and whatnot. But the point is that you need to build the infrastructure first. So on that note, I'm working on this project which is called Stacker Network, which is a SDK for building application-specific rollups. And what it basically does, it does all the heavy lifting for setting up a rollup project. It's fully modular, but also composable. So it allows you to mix and match different variety of things from different places. And it can build rollup in any general purpose language. So right now, it's a common misconception that rollups needs to be like a EVM chain. It needs to run contracts and whatnot. There are some other rollups flavor as well. And also, it's a batteries included approach. So you have sequencers going on. You don't need to worry about that and everything. And that's mostly around it. So this is a very interesting analogy that I have. So you must be aware of Web2 microservices, right? So what microservices does is that they run a specific module and that communicates with other modules, and you can scale these microservices independently. And for this project vision, I envision like that there is a Aave rollup, there is a Uniswap rollup, there is OpenSea rollup, and you can have your own application which is independent. So let's say there is some gas spike on Aave. So Aave can scale independently. Your application won't be affected by it. And these are some of the possibilities that you can build out with the rollup. So you don't need to be situated with you don't need to be fixated with a single choice. So you could build a rollup in React. You can build a rollup in Node or Rust or anything. You can use push protocol for doing middleware stuff. You could use ENS for doing whatever you want to do. You can have a rollup in Unity. You're building a game, you have that module plug and play, and that directly connects to OpenSea, and that module runs on Android. You can do something bizarre as well. You can have an Optimism runtime environment, but that settles on Arbitrum. So this is something which will upset a lot of people, but that's a possibility. So instead of building on an L2, my vision is to build an L2, and that too in a Web2 native way. So you don't need to be you don't need to fixate yourself to building on Optimism or Arbitrum or Starknet or anything. You can just spin up your own L2, and that L2 will be yours to run. And I'm looking for collaborators for this project, so builders and projects. If you're a project who wants to explore this domain, please reach out. If you're a builder who wants to help build this project, also reach out. I'll be there at ETH India as well, so you can come and talk. And yeah, that's mostly about it. Thank you. And if you want to connect with me, that link will take you to my Twitter. And yeah, let's talk. Thanks.
Thanks for plugging in Push. Guys, do you have any questions? Okay. Everyone knows how to build optimistic rollup now? Awesome. Thank you, Kautuk.
Yeah, they have some questions.
Optimistic roll. I have this on. Yeah, I have a question about optimistic rollups and ZK rollups. So there's this trust assumption with optimistic rollups, right? Like all the transactions that are being proposed are like legitimate; they are not faulty. So how does this work with ZK rollup? What's the difference? That is what I want to understand. Because, and like you explained, there's a 7-day duration, like before finality is achieved, and the transactions are irreversible. So how does ZK rollup like go through the process? Like, what's the difference?
Right. So the difference between them is that you build a very sophisticated algorithm which only can move that state to a desired state only if the inputs are correct. So how snarks work is that if you have two inputs and that results in an output, any change to that input will result in a very different output, right? And with ZK, what you can do is you can entirely remove the input and still have that compute ready inside a proof, right? So you don't really need the inputs. You can just use the proof and the output to actually say if the inputs were correct or not. So the idea is that I'll give you an example. Let's say you build a proof for multiplying two numbers. So the number is 12. So how many ways you can achieve 12? You can do 2 and 6, you can do 4 and 3, and you can do 12 and 1, right? So what basically happens in a snark is that you don't care about what those numbers were. You only care about what the computation was. So if the output was 12 and the computation was, let's say, the proof, you can just plug that in and you will get a true or false result out of it. So that's what ZK Rollup does. It doesn't care about inputs. It only cares about the computation, and that computation is stored on chain. So you can just verify that the proofs, the inputs were correct or not.
And these rollups don't have their own consensus mechanism.
They don't. So there is a sequencer. So what happens is that the sequencer, like up until now in the current state, all of the rollups have a centralized sequencer. You trust these rollups to actually do the sequencing for you. The transactions come in and they bundle it. You can verify these, but they are the ones doing it. And they just post the data on chain. This consensus is built on the settlement layer, which is the layer 1. But that needs to change. Like personally, I believe that if we build a consensus at the sequencer level itself, we decentralize the sequencers and have a soft consensus going on, then you can actually reduce the time to finality for optimistic rollups as well. So instead of 7 days, you can say that the consensus has, there's also soft consensus between the sequencer. So instead of waiting for 7 days, we can just do it in 1 day. So
I have one other follow-up. So when you say soft consensus, is it something like what Polygon is doing right now? It has
no. So Polygon, the consensus happens there. The consensus doesn't happen on L1 as far as I know for the POS chain. So I wouldn't comment on it, but the point is, the soft consensus basically means there will be another consensus on settlement. Yeah.
Thank you.